Now we want to explore a new type of function called a rational function. A rational function is composed of a polynomial in a numerator and a polynomial in a denominator. So really you can think of a rational function as being a fraction, right? A fraction where I've got polynomials on the top, polynomials on the bottom. So when we look at a rational function, there's a couple ways that we want to describe it, okay? So the first thing that I want to do is just show us what is a rational function. So if you look at this graph that I'm showing here, this is just one example of a rational function. So a rational function is going to have a couple of things that maybe we haven't seen before. One thing that it's going to have is it's going to have this vertical asymptote, and we'll talk about those in a minute. A vertical asymptote would be this vertical dashed line here. Okay, and what I notice about this vertical asymptote is that on both sides, the graph is approaching that line, right? So if I look over here, I'm approaching and I'm approaching. So one might go up, one might go down, but either way, I will have a graph approaching that asymptote. The graph will go up or down at that point because it's a vertical asymptote and a vertical line goes up and down. All right, notice that it does not cross or actually ever touch that asymptote. And we'll talk about that again here in a minute. All right, another thing that I'll notice is that we have a horizontal asymptote. So this horizontal asymptote, again a dashed line, I notice that the graph is again approaching that horizontal asymptote. It's going to approach either to the left or to the right because a horizontal line moves from the left to the right, okay? So when we look at these asymptotes, one thing that we should be noticing is that it's kind of acting as a boundary line for our graph. Notice that my function here in the bottom, it has to stay below that horizontal asymptote and to the right of that vertical asymptote. So it's kind of bounded there at the bottom. And then I notice my top piece of the function, it's bounded above that horizontal asymptote, and it's to the left of that vertical asymptote. So it's kind of bounded up top there, okay? Now, another thing that I might notice about this is that it's got these two pieces, okay? So when I am looking at a rational function, okay, what's going to happen is I'm going to have something occurring on one side of the asymptote and something occurring on the other side of the asymptote. In this case, I notice that they're kind of on opposite sides, meaning they're kind of, they've kind of followed through a diagonal there. They don't have to. We might see a rational function where they're both at the tops. We might see one where they're both at the bottoms. We might see one where they're diagonal the other direction. Okay, we might see some where there's more than just two of these pieces. So there's lots of different types of rational functions, but one thing that we will notice is that it's got these different elements that we want to look at. Okay, so starting off in a rational function, one thing that I definitely want to discuss is about the domain of this function. And we've actually already done this. Remember when we were looking at domain from an equation? One of our scenarios was that we had a fraction and that the denominator could not be 0. So this is actually one of those scenarios that we've already looked at. So when I'm looking at a rational function, I'm going to find the domain by setting the denominator not equal to 0. Okay, so if I've got an equation, so let's get an equation here. Let's say we have f of x is 3x plus 2 divided by 5x minus 15. All right, and we want to find the domain. So to find our domain, we're going to set that denominator, 5x minus 15, not equal to 0. All right, so then we would continue to solve, so I'm going to move that 15. I'm going to divide by my 5. And so I'm going to say x cannot be 3. So if I wanted to write this as an interval, I would say that it's going to go from negative infinity to 3, union 3 to infinity. All right, so from an equation, all I have to do is take that denominator and set it not equal to 0. All right, let's look at one more equation just so that we can make sure that we've got it, and then I'll talk about from this graph here. All right, so let's say we had the function 2x minus 7 over x squared minus 5x minus 24, right? So again, if I'm finding this domain, I'm going to set that denominator, which my denominator here is x squared minus 5x minus 24. So I'm going to say x squared minus 5x minus 24 not equal to 0. So now this is a quadratic. It's okay, we know how to solve quadratics. I'm going to go ahead and factor. So I'm going to say what multiplies to negative 24 and adds to negative 5? Well, it's going to be negative 8 and positive 3. I'm going to solve each of these. So I'm going to say x cannot be 8 and x cannot be negative 3. Remember, solving, I'd add that 8 to the other side and that kind of thing. All right, so now I'm excluding two values. If I wanted to write the domain in interval notation, I'm going to say it's going to go from negative infinity to that negative 3, right? Think of a number line. I'm going to jump over negative 3 and go on to 8. I'm going to jump over 8 and go to infinity, all right? So I'm setting that denominator equal or not equal to 0, and then I'm solving. Now, if I'm looking at an equation, all I need to do to talk about this domain, remember domain is the x value, so I need to see what x value I'm excluding. So one thing that we want to look at is going to be this vertical asymptote, right? Because we notice the vertical asymptote is what is on the x axis, right? It's going to cut through the x axis, and no matter where I am, we know that I could not ever be that value. So if I was trying to find my domain from this graph, I would actually say that my domain is going to go from negative infinity. It's going to stop at negative 2, jump over negative 2, right? Because I'm negative infinity all the way to, oh, I can't be negative 2. Then I pick up from negative 2 all the way off to infinity. So all I need to do for the domain, if I'm looking at a graph, is to find where that vertical asymptote is, and I'm going to use that number in my inequality. Okay? So I can now find the domain from either an equation, denominator not equal to 0, or from a graph, I find that vertical asymptote, and that's the number that I would use.